the power -6 meters. And what I say, it has given that 1/10 of human hair. But if you will see, if you will check it in some of the books, they have reported it is nothing but, suppose you have taken a hair of a human. If you have taken a human hair, and on the dimension side you are going to cut it into 70 to 100 times, just make it or fix a number that is just 70 times. And in that case, out of the 71 part, if you are taking, that is nothing but that 1 micrometer, that diameter you will be getting. So that small it is. If you will go to that nano thing, it is again, it is going to 3 decimals. Again, that is the 3 decimal, that is your 10 to the -9. So it is quite, it is in terms of your human eye, it will be quite invisible, the things. Okay, so what it is the products, what are the products it is coming? If you will talk, then that is your microsensor thing. You will be having the acoustic wave sensors, biomedicals, chemical sensors, inertia sensors, and optical, pressure, radiation, thermal. There is a long list is there, because without this micro sensors or micro actuators, nowadays you cannot move a single bit of your life. Why? Because if you look to your smartwatch, in that case, each part, it is consisting of either it is detecting your what is the the when it is vibrating, those things it is checking. Then in those cases, it is checking the micro sensors. In your mobile thing, either it is showing that direction. Okay, so in every devices, either your mobile or smartwatch, in everyday life, whatever we are using, in that case, the microsensors and actuators are very huge role they are playing. So in terms of microactuators, what are there? Valves are there, pumps and microfluidics are there, electrical and optical relay and switches are there, grippers, tweezers, tongs, smart tongue. Okay. Okay. So if you will see, there is a tweezer and tongue is it is saying, what is that meaning? What is the meaning of this tongue is there? If you will see if you will look to so okay, now I'm coming to this one. On internet, or there is a IEEE transaction paper is there on smart tongue. So what is this smart tongue is there? So suppose you will be taking a device, okay, and you are putting, suppose because if in India, I will be telling one story for this thing, because when we are going to this technical thing, then we need to know what is the in practical use, what is the use of this thing. So in Assam, they used to produce the tea, and what happened once they have exported the tea in a in tons of the tea, it is export to US. And when they at that import section of US, they detected that there is huge chemical is used for the production of those tea leaves. So because of that, they abandoned that thing. And when they will return back the tea leaves, okay, then that will be of a huge loss. That's why everything they dumped in the sea, in the ocean. So that's why now it is required the tongue. What is not that tongue? Smart tongue. In that case, you are going to take that leaf thing, and in that case, you are putting at the sensor, and with some liquid or with some what are the liquid is provided, prescribed liquids, and you will be testing whether what is the required amount of chemical is there or not. Suppose it is more than the threshold voltage. Suppose they are saying that up to 70% is acceptable, but your the T which is there, it is of 90%. Then definitely they are going to abandon that thing. So that's why the smart tongue it has come into picture, and in you will be getting these things. So after that, it is coming to the linear and rotary motors. Okay, there are so many motors it is available nowadays. like your printer head, how it is moving. So with the help of your micro motors only. So just like if you will see in case of your read and write heads, it is the one of the application it is saying. Then inkjet printer heads are there, micro device components are there. So these are the some things I have given you the introduction thing. Okay, so this is nothing but how the miniaturization is playing in our daily life. Small system tends to move or stop more quickly due to low mechanical inertia. Okay, these things are there. What happens in this case, we will be able to see the precision movement we need to see. And okay, so these are the small thing it is written. I will come to this thing. So this one already I told you what is that introduction to micrometer. What is the meaning of your micrometer thing? What is the meaning of this nanometer thing? So micrometer is nothing but your 10 to the power -6, and nanometer is nothing but your 10 to the power -9. So what it is saying, initiated in 1947 with the invention of transistors, but the term micromachining was coined in 1982. What is that micromachining? In further slides, we will be able to see. So in this case, so it is so there are two ways to we are going to fabricate. That is your top-down approach. Another is your bottom-up approach. So in case of a bottom-up approach, that is inspired by Richard Feynman, and it is in 1959 with active R&D began in around 1995 thing. Okay, so this is fine. Okay, this is fine thing. Now this is the what is the if we will be involved in that research area, if we will be going to do some research in that area, whether there is career for us or not. This one is the first question. Then only we should proceed in that area. So if we will say nowadays IoT, if we will say machine learning, yes, there is a the market is trending in that direction. Just like that, if we will look to this MEMS and NEMS thing, the market value, what is the market value is there? It is in 2001, it is around $50 million was there. Then those things are they predicted, and it has completed. In 2003 they were predicting something $26.5 billion. So it is the story of a long back. Now we are coming to the projection in terms of your 2026, because now we are at the end of 2020, and we will be looking to 2026 thing. So this is very recent the very recent information. That is what it is saying. The global microelectromechanical systems, which is nothing the MEMS market, is the size valued at $48.74 billion in 2018. That is 2018 year. That is the thing, that is the value thing. Now it is projected how much? It is like 122.83 billion US dollar by 2026. See, there is a huge jump. There is a huge jump. So because if it is jumping, then definitely we should be able to get the benefit of that thing. We should be able to contribute from our side where they will be using. Definitely everything it is becoming the smart thing. If a system it is becoming smart, then definitely it is requiring the MEMS thing, the MEMS sensor, the MEMS actuator. Those things are required. So that's why an enormous opportunity for the manufacturing industry it is there. And if anybody it is interested, they can start with today only they can start doing this in research in this area. Because why I'm saying, you can see this thing. Even if you are not believing, then definitely you search it on that internet, and you can get the data, and you will be convinced with that thing. So this is also a small introduction. That is your the global MEMS market, how it is divided. So if you will say, this is your sensor thing. In terms of your sensors, that is your inertial sensors are there, pressure sensors are there, optical sensors are there, environmental sensors, ultrasonic sensor. These are quite few categories it is shown, but there is huge segments are also there. Okay. Then in terms of your actuators, that is your optical MEMS, microfluidics, RF MEMS, there are some micro speakers are there, ultrasonic fingerprints are there, so many things are. Next segmentation is nothing but the application bit. What is that thing? One is your consumer electronics, second is your automotive, third is industrial, aerospace and defense, healthcare, telecommunication, so many things it is coming. If you will see which one you are going to leave it, consumer electronics, you cannot sustain without this thing. That is nothing but your watch, smartphones, those things it is coming in picture. So automotive, you know that thing. In automotive thing, in vehicles also, every time the the indicators, or in case of your suppose I will be saying that in four-wheelers, in four-wheeler, can you just imagine how many sensors they are using, where they are using, how many actuators are they are using, that like micro level of thing. So I told you, if you will go for the four-wheeler, main thing is nothing but your how much air is there in that tires, then definitely for that they are using this pressure sensor, and that is of your micro level of pressure sensors. Then if we will come to suppose you are going for micro, the cameras are there. In that case, you are, because in cameras when you are going to park it, and in that park, so one example is the tire thing, second is in which direction that tire is there, for that also these micro sensors are using, and in that way they will show you that whether the tires are kept in the straight thing or it is in some angle, it is inclined, because with that thing also you will be facing some accident. It can be you can avoid it. Okay, then it is coming to industrial. In industrial thing, mainly it is going for the automation thing. In case of your automation, definitely you require these sensors and these actuators. Aerospace and defense, see, if in nowadays if you are involved in research of this MEMS, specifically in the aerospace or defense, then and you are getting some some innovative work with your research thing, and you are going to get some patent thing, definitely you are going to be millionaire or billionaire, because that thing, it can go with your the royalty you will be getting out of that patent. That is huge money. If you are selling that thing also, it is a huge money you are going to get it. If not, then you can go for the startup. Suppose you have developed something and you are going to do some production part of that thing. Suppose one sensor you have developed and you know that it is going to play a big role in that market, a huge role in that market, then definitely you should go for the production of that thing. Definitely you require some help, because you cannot set up that production part, but you can take some help from some industries and you can start producing that thing, and you can level it with your name and you sell it. Okay, and otherwise directly you can contact to whoever the companies involved with the production of this defense equipments, or start doing this thing. Healthcare, because see, this MEMS sensor thing, I told you, main thing is, what is that healthcare? Either you can go for your neuro sensor things are there, heartbeat sensors are there, blood pressure sensors are there, everything it is coming, because these are the small examples and you are quite aware of those sensors I'm telling you. Okay, there are some other thing, means other sensors there which are, means even we are not able to, we have not known those things, we have never heard those things, but still those sensors are there. And telecommunication, it is a huge role it is playing in our lives. Now it is by region thing, who are the players in that global MEMS market. If you will see in North America, US, Canada, Mexico. Then in case of Europe, in UK, Germany, France, Italy, rest of Europe. What is that thing? Because in these areas, either the production is done or the consumption of your devices, those things are same. Then it is coming to Asia Pacific. Definitely the China is there, Japan is there, India is there, South Korea is there. Okay, so they are the key role players, because in case of see, in India, we are not able to, hopefully, because we are producing some of the devices of this micro and nano technology devices, but as per my knowledge, there are not such huge production companies. Okay, but in case of your China, Taiwan, they have those things. Okay, and out of that, and in India case, what we are there, suppose in terms of your Samsung is there, Samsung Delhi, they used to do the research in this MEMS areas. Okay, and what they are doing, basically they are providing the foundation ideas how the device will be, then they are giving the simulation results and how the structure will look like. In South Korea, they used to produce it. That's all. That is also one of the big thing. Okay, then so Latin America, Middle East, Africa, so these are the in segmentation thing it is coming. Yes, this one I got it from the net, and I have cited this one. So what it is saying, global microelectromechanical system market. So what happens in by 2018, it is the top layer, it is there, that is the quite blue thing, and by 2026 it is showing in terms of a little bit green thing. Okay, so the backside picture, what it is saying, it is the increase in adoption of wearable devices and innovative application in biomedical sector. One example I will be providing you. Nowadays, see why it is saying that adoption of wearable devices, because now in our older days we used to wear that watches. Okay, the watches only when we are going out, or like looking to the time only. But now the smartwatches, they are using for all purposes. Either they receive the call, either they will knowing that what call it is coming out, and looking to healthcare. In healthcare, what is the blood pressure is there, and nowadays one trend is there in iPhone, in Apple watches, they have given that what is the some oxygen level is there, something it has shown, some new technology they have came out. And now second thing I'm saying, in bed we used to use the normal bed, either it is the wooden thing or the some metal thing bed we are using. After that, so in that bed, if you are using that, in that case, suppose we are using some sensors. In that case, if you might have seen that one of the advertisement it is coming nowadays, in that case, according to your shape and size, the bed will be trending, or they will be keeping that size. If you are falling asleep, then it is going to detect what is the temperature it is going on, and if there is a fluctuation is there. Yes, those things are very important things they are playing. So it is one of the biomedical sectors it is coming. Then emerging trends towards autonomous vehicles, those things already I have discussed. Incorporating the sensors in devices incurs extra value and reduces life of device. Then emerging trends in automotive industry, the increase in popularity of IoT, lack of standardized fabrication process. Yes, this lack of standardized fabrication process of MEMS, this one need to be standardized. If you will see, there is one slide is there, I will show you. In that case, MEMS and microelectronics, I'm showing you what is the difference is there. And in that case, we will be see that there is a huge scope for us. Now, if you will be involved in that thing, I know, because once we are involved that thing, then if we don't have that practical, suppose experiment things, facility is not there, then we are quite getting demotivated out of that thing, and we are leaving the research area. No, it is not that way. You just find some other way to do the practical thing, experiment thing, and in that case you can able to see that thing. So what is there in MEMS thing? Till now the fabrication process is not standardized. If you want, and if you will be putting a mark, or in that case it is going to be standardized. Suppose you are developing one sensor, in next day I will be developing the same sensor with some other way of fabrication process, and that will be quite cheaper and taking less time. Then definitely my process will be, it is going to be, people are going to adopt that thing. So that's why it is not standard thing. But in case of the microelectronics, it is not like that way. In case of your the design of your ICs, chips, in that case everything is till now it is standardized thing. Okay, these are the some evolution microfabrication when it has started, like 1947 it has started thing. Okay, so okay, now yes, this one I was talking like though if you are not able to see, people will be confused with what is the, I know I am working in microelectronics, then what is the use of this MEMS thing? Okay, so now there is a, comparison is there, or there is some difference between this microelectronics and microsystems are there. Basically, this microsystem is nothing but your MEMS thing. And what I'm saying, this MEMS is nothing but based on either the silicon thing or the piezoelectric materials, everything. Now, what for the I have given one standardized thing. What happened if you will look to this one? It is saying the silicon based. Why? Because what are the microelectronics it is doing? Everything is the silicon based your devices it is making. So first thing, it is saying that primarily it is that two-dimensional structure. If you will see your ICs, see what are the ICs you are holding in your hand, they are, you cannot see what is the structure is there, because it is the cover of one plastic cover is there. That what are the black you are seeing, you just check it in terms of microelectronics. Very easily available thing is your 8085 is there. Check it. In that case, you are not able to see what is the structure inside is there. Okay, if you will crack it also, because you are going to see, so in that case you are going to damage that thing. And if you will see only the terminals, you are able to see that thing. Okay, but you cannot see the structure. Now when it is coming to microsystem, it is a complex three-dimensional structure, because in MEMS thing you will be find that the devices are moving, they are running, they are rotating. Those things you will be getting, like a small gear system. If you will see in the first slide, I've shown you one gear thing. In that case, that is the MEMS thing, it will be rotating thing. Okay, so that's why it is of your three-dimensional structure it is there. In microelectronics, it's the stationary structure, and in case of microsystem, it is a involving moving components. What is the stationary structure? Either the FAT thing, MOSFET devices are there. So suppose I'm saying that one IC, you will take it, it is involving of your capacitors, your resistors are there, then FAT devices, MOSFET devices, those things are there. But when it is coming to microsystem thing, it is involving some moving parts. Okay, just like your gear thing. In case of your actuators, there will be some piezoelectric devices, it is moving. So these are the things. This is the one of the major differences there. Now, if functional way, if you're coming, it is nothing but transmitting electricity for specific electrical function. Whereas in case of a microsystem, it is performs a great variety of specific biological, chemical, electromechanical, and optical functions are there. So if you will check it, this one, IC die protected from conductive media, then delicate. Okay, so there is a huge list is there. Okay, if you will check it, and I will be providing you the slide, you can check it. So how you will be knowing? So first thing is your two-dimensional, three-dimensional, stationary structure, moving components. Okay, what it is doing, and this thing. So this way it is going. And you see this one, fourth one, you just check it. In this case, it is saying that it uses single crystal silicon die. So that is nothing but for the fabrication of your ICs, it is using only a IC wafer, means silicon wafer it is using. And with that thing, what are the extra silicon compounds and some plastic materials it is using, and it is producing that device. But in case of your MEMS thing, it is not the same. It is involving means apart from this silicon dies, it is using some other devices also: gallium arsenide, quartz, polymers, ceramic, metals, piezoelectric materials like your lithium niobate, lithium tantalate, PJT. So many things it is involving. And if you will come to the next point, it is something like fewer components to be assembled. Okay, then it comes to next point. It is mature IC design methodologies are there. That means whatever the fabrication technologies are there till now, those things are standardized. That means if a specific, yes,
Hello.
yes,
In piezo crystal,
yes.
Whether natural crystals are used or synthetic crystals are used more reliable?
No, actually, if you are going for, I cannot say that natural thing or this thing, because there are some standard substrates are there. And we are using for till now, what are the things I have used? I'm saying the standard, like lithium niobate I have used, lithium tantalate I have used. Those things standard produced thing, and that is man-made, means composite things it is done. Okay, not like natural thing, because we have already purchasing. Because see, what are the things we are saying in natural case also, we need to modify some of the characteristics for the better piezoelectric characteristics, to get the better characteristic thing. That's why it is required to modify some of the basic the characteristics thing. Okay, so now what I'm saying, in case of your IC thing, it is the process are already standardized thing, and in this case lack of engineering design methodology and standards are there. So these are some of the things it is there, so you can check it, because it's around 120-30 slides are there, and I will be coming to little bit faster thing. Now it is coming to who are going to be involved in this case, multidisciplinary nature of microsystem engineering. What is that thing? If we look to this one, it is having electrochemical process. So there is a top, that is a natural science, physics and biochemistry it is there. Then electrochemical process is there. Then in case of electrochemistry process, it is involving the electrical engineering, like power supply, electric systems for hydrodynamic and signal transduction. Then electric circuit thing, integration of MEMS and CMOS thing. Then second part, it is coming to, so it is nothing but a hierarchy. It is showing what are the different backgrounds it can be able to involve. If you will see it, one is your electrical engineering, second is your mechanical engineering, third is your material engineering. And with that thing also, in mechanical also, it can able to see use that chemical engineering thing, and in this case industrial engineering. So in that case, in electrical thing, what are the we are going to use it and how it is. So it is nothing but the from the production to implementation, what are the things we are going to use it out of the electrical engineering it is there. So if we will come to that chemical engineering, what it is helping, it is helping in terms of your microfabrication processes. There are so many chemical compositions are there to etch something. Suppose a device is there and we required a type of hole we require, then with some chemical composition we can able to strike it and able to dig it, or that is nothing but called as the etching thing. Or suppose we want to coat something, so like that way thin film coatings we can able to do with this chemical engineering process. Then mechanical also, it is like precision machine design, mechanism linkages, those things are there. In industrial thing, it is nothing but what the process design, so it is nothing but optimizing what are the processes. Because suppose for producing one device, in one method we are taking around 8 steps, so it required 8 different steps are required. But in other way, the same device we can able to make it with the help of 6 steps, so around 2 steps it can be neglected. So that way we can able to optimize things. So that's why I'm saying that it is not the standardized till now. Okay, so this is fine. This is I think some of the data. It is what it's saying, commercialization of MEMS and microsystem. Mainly the airbag inertia, where it is used for your vehicles, for the safety balloons it is using. So it is of your it is, I think it is a quite old data only, because it is far that more than that this thing it is there, like airbag inertia sensors at 2 billion units per year. It is, they are selling in the market, they are selling 2 billion unit of your airbag inertia sensors, and manifold absolute pressure sensor of 40 million units per sensor. So like the blood pressure sensor, see blood pressure sensor nowadays everywhere, every time we are using. So it is not only 20 million, it is many more times than this 20 million times it is using. So old MEMS is pressure sensor, accelerometer, other MEMS, and new MEMS is BioMEMS, IT MEMS for telecommunication, opto-MEMS. What is this opto-MEMS? It is nothing but now it is called as the MEMS, micro optical electromechanical system. MEMS is there. So, and RF MEMS. BioMEMS, it is now it is occupying the market, because if you are integrating little bit of with your biotechnology, then definitely you are going to fetch some good projects. Even in case of your India, SERV or the DST, if you are showing some results with the help of your biotech also, then definitely it is going to fetch some of your good projects proposals. Yes, this is some of the history it has given, like when it has started. Basically it has started with your 1947 at the Bell Laboratory. Then with the chip thing, it has started with your this your 4004 IC thing in 1971. After that, yes, yes,
In the top two names,
yes,
with the fiber optics are used for opto MEMS.
yes. No, no, fiber
Fiber.
optics, fiber optics, it is the thing. But when we are going for this MEMS thing, no, then we are using some channels things. Okay, so yes, you that the idea of this fiber optics, it is required for this opto MEMS thing. Fiber optics thing idea is required, and with that thing we are going to blend that thing. We are going to blend it in our application procedure way. In terms of application thing, when we are coming, then how you will be using, suppose that MEMS thing we are using for the communication purpose. Okay, one signal we are going to transmit it. Okay, so one of yes.
My question is, miniaturization is possible in fiber optics?
uh, it is nothing but the channel thing. Yes, it is, because in case of your MEMS thing, what I'm saying, yes, I got your question whether they are using for this miniaturization is possible or not. So we are looking not only that optical fiber thing. In optical fiber also, suppose in that case we require in that optical fiber thing, in a section we required a device to enhance the signal thing. So for that case, we are going to use that MEMS devices involving that that optical application thing. It is not only that that optical wire is there or that thing is there. In that case, for enhancement of your signal, we are going to use this MEMS thing. So this MEMS device, when we are designing, then we need to keep the idea whether how it is going to match with the application of that area. With that thing, it is going to make it.
Okay. Okay.
Mr. Sangram Singh, Sangram Kishore,
Yes,
please,
sir.
I request, please let them complete, and you take a pen or paper and put your question on that pen paper and ask the question in the end of the session.
Okay.
Because this type of interruption, there is a mind diversion of the speaker.
Okay, 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 sir. Okay, thank you, sir. Okay.
So note that question and you put in the last question answer hour.
Okay, okay, sir. So okay, fine. These are the some of the history thing. It is there. I'm not going through it. Just I have kept so that when I will distribute this thing, you can able to watch it, check it. Then it is coming to the list includes exponential growing use of your computers, internet, portable electronics, cellular telephony, digital photography. So this is also one of the listing it has given. Just like in that case, if you will come to the sensor part, what are sensor? It is nothing but capacitive, piezoelectric, piezoresistive, electronic resonance, optical detection techniques. Now it is coming to advanced features. For integrated pressure sensor, it includes built-in vacuum for absolute pressure measurement, integrated telemetry link, closed loop control, insensitivity to contaminants. Okay, so okay, fine. This is also one of the, it is used, it has shown that is your inkjet printer head, it is there. It is the MEMS chip is there. So where it is going to control it. See, if you will check it, it is not the schematic side view of the inkjet chip with the fluid nozzles. It is nothing but the with your pressure thing. It is going to provide the ink thing, and with that ink, it is going to provide different colors also. Like RGB we are taking out of that different colors it is. So with the inkjet printer, when we are printing, then definitely it is going to be useful. Okay, so this is also one of the thing it has given. Okay, okay, fine. I just go through that thing. Okay, fine. Now it is coming to okay, smart writing instrument. This is also history thing. Okay, now it is coming to this one, because those are history things only, so I have skipped that thing. Representative major branches of MEMS technology. What are the major branches are there? Area of research and the perceived drivers of technology. If we will come to the optical MEMS, it is nothing but monolithic integration of your mechanics, electronics, and optics. After that, unique spatial or wavelength tunability, improved efficiency of optical assembly and alignment accuracy. So that is in terms of optical MEMS. When it is coming to bio-MEMS, it is miniaturization is required, minimum invasion, and size match with the biological entities. Just like if your antigen antibody will be kept, suppose I'm detecting some blood, a sugar thing. Okay, so in that case, this bio-MEMS devices will be used. Okay, so in that case, it can use that chemical thing and your blood thing. Out of that, it is going to show you how much sugar it is, percentage of sugar it is there. Then it is coming to microfluidic. It is nothing but your reduced amount of samples and reagents and associated cost is there. So this is nothing but diverse technology are there. Now, in case of your RF MEMS, it is unique performance not found in solid state RF integrated devices. Promises of direct integration of active and passive elementary with the circuitry. Then NEMS is a unique physical properties due to scaling, because it is nothing but going to very minimum scale, that is your 10 to the minus 9 meters. So example, ultra low mass and ultra high resonant frequency things are there. Though, because what is that ultra high resonance frequency? When it is the device size it is going down, that time the frequency it is going up thing. So if the micro level, if it is in terms of megahertz, it is working resonant frequency, then in terms of your NEMS, it is going with your like gigahertz scale. Okay, so still it is working, it is going with the history thing only. So what it is saying, the MEMS components, it is nothing but binary optical lens, diffraction gratings, tunable optical mirrors, interferometric filters, phase modulators, and adaptive optics, tunable filters. These are the new, these are the some of the names. You should be here this thing, gas spectrum analyzer, then network routers. Okay, yes, this is one picture it has shown. If you will see, this is the scaling of your 500 micrometer is there. So if you will check it, micro machine optical components are there, A, B, and if you will not able to see it, then I will make it. Okay, so just check it. This is your, okay, right. Fine. Okay, now it is visible, I think. Okay, yes. So binary lens, vertical diffraction getting is there, 2-axis scanning micro mirrors are there. So these are the some of the pictures it is showing, and I will coming to this thing. Okay, this is a okay, this is one of the capillary electrophoresis, that is the C network system for biomedic analysis. What is that thing? If you will, I will just a little bit describe on this thing. So here we are going to mix two liquids. In case of your biomedics, suppose we need to add two liquid things. So what is this thing it is showing? So there is a and this is your B thing. What happened in this case? Analyte reservoir, and this is the buffer reservoir is there. In the left side picture I am discussing. So here one liquid you are providing and another liquid you are providing this thing. So these are the fluid channels. It is of your the channel size is very, that is nothing but in terms of micrometers it is there. And a simple capillary tabular network, so that is of 20 by 30 micrometer thing. When it is going to put the liquids here, in that case at the center point, that is the plug thing, it is going to check it. It is going to mix that thing. Okay, and with the injection channel it is going to go for the best thing, and this side it is also. So here it is going to show the results thing how it is. So this is on the function thing I'm saying. Here if you will check it, the device how it will look like, it is the channel thing. If you will see that thing, one side your will be your inlet will be there, and the reservoir will be there. So okay, so in this case, so you see this top polymer cover which is there, it is already attached thing. To conveniently show the idea how it is fabricated, it is just taken out. So with that thing, top polymer cover and bottom polymer cover, it will be ATA's thing, and what are the processes of your mixing up different chemicals or liquids, it is going on inside that thing. So this is also one of the micro machine tunable capacitors, okay, and inductors are there. Okay, so these are the future trends. It is, see, till now I'm in the introduction part only. I have not gone to a specific thing. So what it is saying, in the next 10 years, the MEMS research field is expected to grow rapidly. What already I have told this thing. So more application will be emerged. I told you, with the help of your robotics, medicine, augmented reality, actuators, this thing, it is going to emerge. Like rapid and yet sophisticated system design will be reality. So MEMS designs methodology and know how it is maturing. Okay, so now the degree of design sophistication will continue to increase. Okay, fine. So these are some of the things. Electronic functional integration will continue. So MEMS devices will further enjoy the benefits of circuit integration. Yes, this is quite challenging thing. If you will see the first line, it is saying, what happened, suppose you are developing one a sensor and you want to integrate, or you want to integrate with a IC thing. As per my knowledge, by 2010 or 2010, by that time also, when the integration they used to do, it is like just a plug in and plug out type of thing. But what the idea is, directly you will be taking the IC and you will make a covered thing, and you will process the same silicon substrate for development of your a sensor thing. So what will happen, directly it is going to be connected. So it is not that a separate sensor, it is connecting with the IC thing. That's why if you will be able to make it, that is your MEMS devices will further enjoy the benefits of circuit integration, allowing electrical, logic, computational, and decision making functions. So then it is coming to ability to make and manufacture MEMS products will continue to improve. Okay, then it is coming to MEMS production will migrate to larger wafer sizes. Okay, compression will intensify. Yes, so here it is coming to different categories we are coming. So what is that thing? If you will see energy domain, the MEMS things also, in MEMS thing we are developing mainly two things, that is your sensors and actuators. In that case, it is involving some energy domains and transducers. Who are they? How they are different? So that is nothing but the 6 major energy domains are there. One is your electrical domain, mechanical domain, chemical domain, radiative domain. They're the energy domains. Magnetic domain, thermal domain. So this is the way it is categorized. If I will come to from the bottom, I will start it. Electrical, it is involving, when you are developing the MEMS device, it is involving voltage, current density, resistance, capacitance, inductance, those things it will be involving. Like that, in mechanical thing, force, pressure, speed, flow rate, viscosity, acceleration, then your gravity, touch, acoustic, vibration. So those things it is involving. Like in terms of your thermal, it is involving temperature, thermal conductance, heat flux, heat capacity, phase change, calorimetry. So like that, magnetic field strength. So this way it is nothing but different energies it is using. Mainly, if you will check it in case of chemical concentration, pH values, reaction rate, molecule recognition, DNA sequence. So basically this chemical is nothing but little bit blend with your biotechnology also. Then radiative, electromagnetic waves, infrared radiation, UV radiation, those things. Okay, simple thing, how it is functioning. If we will say, I will say that yes, so many things we have discussed, then a simple directly work thing will come to picture. So in that case, a microsensor, how it is working. If you will see, there is a input signal is there, then another side output signal is there. So here you are providing something, and this side you are going to see this thing. What it is doing? It is nothing but micro sensing element it is there. Suppose a pressure sensor is there, micro pressure sensor. In that case, input is nothing but what are the pressure you are providing with your hand or thumb or with some other devices. So that pressure, suppose how much Newton of pressure it is provided. So that is deciding with this micro sensing element. How it is there? So there are so many devices it is there. I will show you. Next, it is going to, so that pressure thing, it is need to be in order to see that thing, it need to be convert to in terms of your electrical thing. Then only that is nothing but transduction unit it is doing, and after that it is going to show with the output signal, and the transduction unit will be functioning with the help of your power supply. So this is a structure of your sensor, a micro sensor it is there. So like that, in this case, again, the same thing it is coming. What are the two categories? One is your physical sensor, another is your chemical or biological sensor. In case of your physical sensors, force, acceleration, pressure, temperature, and flow rate, acoustic vibration, magnetic field strength, those things it is coming. When it is coming to chemical sensors, it is nothing but used to detect chemical or biological variables, including concentration of your chemicals. I told you this is the blending of your biotechnology, so that's why biological variable. So pH, binding strength, biological molecules, protein interaction, those things it is there. If you are going for, so this is quite deeper thing if you are going. So how you are going to decide a sensor? Suppose you are developing a MEMS thing. What are the things you need to deciding? One will be your sensitivity. How much sensitivity it is having. The sensitivity depends on the ratio between the magnitude of output signal and that of the input stimulus. Second is the linearity. If the output signal changes proportional with respect to the input signal, the response is called as a linear. So whatever the input pressure we are providing with that thing, how much voltage it has changed. Okay, suppose 1 Newton means, suppose I'm saying 1 Newton of pressure I have provided. With that thing, whether if it is showing that yes 1 volt thing, and with 2 Newton 2 volt thing, so that is the linear scale it is showing. Accuracy, definitely this is very much necessary for any device. It is not only the sensor or actuator. Any device you require, you do that accuracy is the main concern thing. Ability of a sensor to provide results close to the true value. So whatever pressure I have given to the pressure sensor, the same thing it should be able to show in terms of voltage, current, okay, the digital display thing. Precision, the ability of sensor to give same reading. Definitely if I'm providing with the same energy, it should be able to show that 1 Newton. Okay, it should not, because same pressure I'm providing one time, it is showing 1 Newton. Second time when I'm providing that thing, it is showing that 5 Newton. That's why the precision should be steady. Then responsivity, resolution, then noise thing, noise should be minimized. Okay, and dynamic range, the dynamic range means it should have the highest and lowest. There will be a huge gap should be there. The dynamic range is the ratio between the highest and lowest detectable signal level. Okay, so these are the bandwidth, drift, sensor reliability. These are the necessary things which are required to decide your sensor. Suppose you are developing a MEMS sensor, then these are the parameters which are deciding whether your sensor is a valued sensor or not. Crosstalk or interference, then development cost and time. How much time it is taking, how much money it is involving. The less money, the less time, then definitely your in the market your device will be, it is a boom. So that's why fine. Then it is coming to the actuator part. In this case, simple thing, it is nothing but we see, if you will can remember the how the micro sensor it is working. In that case, input was there, output was there, and all other micro the sensing technology will be there transfer. But in this case, there is nothing is there input. Here directly your power supply is there and some transduction unit is there. After that, it is doing the actuation thing. Directly it is going to show you the output section thing. So it is of your micromotor produced by Liga process. It is there. Okay, so this is one of the micromotor thing. Gears are there. This is the starter is there. These are the rotors are there. Okay, so these starters are made up of mainly the piezoelectric thing. Okay, and mainly then it is coming the rotor thing. The middle part it is going to rotate, and these are the torque transmission gears. Okay, so just like your sensor thing, in actuators also we are considering when it is coming to, just like there are so many parameters were there. So in this case also, torque and force output capacity, range of motion, dynamic response speed and bandwidth, ease of fabrication, ability of material, power consumption, energy sufficiency, linearity displacement, cross sensitivity, footprint. So those things are there. Fine. Now I will skip this thing because I will come to, okay, I will come to the direct part. Okay. So these are the things I told you. Whenever you are sitting idle or something, then you start thinking, in suppose a vehicle will be taken, then what are the sensor it is going to use it. So fine, I will come to directly. Okay, this part I will study because those are the introduction part. I'm directly coming to this MEMS actuator. Sensor part, you got some ideas. Actuators also, you got some idea. Basically, in the MEMS actuation, there are mainly 4 ways are there. That is your electrostatic way, then second is your thermal, third is your magnetic, and fourth is your piezoelectric thing. So these are the different things are there. With that, the MEMS actuation principle it is using. Now, if you will see what is that electrostatic actuation it is there. So that is relies on the attractive force between 2 conductive plates or elements carrying opposite charge. If you will see it, that is nothing but one fixed plate is there, and when we are applying with some voltage thing, it is going to move it, and with that thing it is going to provide some force thing. So it is nothing but the attraction between the oppositely charged conductors, it is given with the force thing. So what is the use of this thing? Directly small examples. See, this is one of the cantilever it has given, and nowadays you know that cantilever it is used for so many applications. Even in IIT Bombay, I think Nanoelectromechanical, one company they have produced. Professor Rao, he is now director of IIT Delhi. He has also introduced that thing, that company, when he have visited to IIT Guwahati. So what they have done in that cantilever thing, simple, they have given some antibodies, and with that thing, what is the sneeze thing, the nanosneeze? Suppose a person, he is carrying some bomb or some explosive materials with him. Then in that case, if we are unable to detect that thing, then this sensor, if we will take the sensor near to that person, that time the air which is bearing some chemical part of this explosive elements, they are coming and sitting on that cantilever thing, and with that thing they are going to detect. So this is one of the application, and it is nothing but converted into one of the startup in IIT Bombay. So that is the Nanoelectromechanical, you can search it. So this cantilever thing, it is nothing but one side it will be fixed, another side it is going to be movable thing, and it is with so many applications it can able to make it. Next, second one is very interesting. If you will check it, there are 2 bases are there. One is your fixed ground plane is there, and at the top there is a fixed beam is there. So, and in between them there is a air gap is there. Now tell me for what purpose it is going to use. In that case, we are providing some voltage drive, something we are providing. And this one, if you are going to provide some force to that one, then it will be used for the pressure sensor thing. How it will be? If you are providing some pressure to the top of this thing, what happens? The gap between them, the air gap, it is decreasing, and with that thing, the capacitance it will be detected. So with that thing, it is going to detect that how much pressure it is it is experiencing. So that way, it is one of the example is there. Then COM drive. This is if anybody can tell me what is the application of this COM drive. This COM drive is nothing but one side you are fixing the electrode fingers, another side you are moving this electrode fingers. Where it will be used? It is nothing but your safety air balloons, the accelerometer. What is that thing? If you are putting one COM drive in x-axis, another in the y-axis, that one is a horizontal and vertical thing, then we can suppose there is if the vehicle is moving and it is detecting some object immediately. So then at that time, the gap, this COM drive, it is going to move ahead, and with that thing, the capacitance thing, what is the F is there, or the capacitance thing it is experiencing, that is going to change it, and with that thing it is then going to detect it. Yes, some place it is means some obstacle it has detected. Okay, now so these are the some of the advantages, disadvantages, and applications are there. You will see there are beautiful pictures are there. So these are the some of your fabrication technology we are using, and gyroscope is there, RF MEMS it is there. Okay, then thermal actuator. So again, in this case, we are using that thermal BIMOF we are using. One side is your thinner plate we are using, another side is a thicker one. When the temperature is provided this side, then because this thinner side it is going to bend fast, with that thing it is going to provide us some actuation thing. Now in this case also some of the advantages, disadvantages are there. So MEMS thermal actuator, it is looking like this one. It is applied, the application requiring high force reliability using robotics applications. Okay, so this is the chevron type of your actuator it is given. If you will see, this is the single buckle beam actuator. So if more than one actuator array is connected, that is your microstructure. This is the common mode current, that is your multi buckle beam actuator it is there. So what happens, it is nothing but your temperature bay it is going to change the thing. Yes, so okay, so these are the some of the things. Yes, someone is saying something. Fine. So this thing, this magnetic actuator, magnetic is there, and this SAP memory alloy. So this is nothing but in remembering the SAP. I'm directly going to that video thing, because here I will be showing you one of the application thing, the starting the foundation of your idea, and how it is going to in practical way how we have converted this one. So this one is quite popular, and when the piezoelectric material it is detected, from that time they tried to do some work in this area, this piezoelectric thing, but in 1949 onwards they have started working. What happens, this piezoelectric device, it is having two properties, that is your direct piezoelectric and another is your converse piezoelectric. So sorry, in case of your direct piezoelectric, when you are providing some pressure to your piezoelectric material, it is going to generate some electric field or the current thing. Converse is the opposite one. When we are providing some voltage to the piezoelectric thing, that time it is going to give some displacements. Okay, so for some of the histories there in 1880, the Curie things they have developed this one, like that thing. And what are the things it is using? It is nothing but your lithium niobate, lithium tantalite, langasite, quartz. These are the different piezoelectric materials are used. Okay, it is specifically I've said for the saw, but it is used for the development of the actuators. What are the problems are there? The stability of piezoelectric ceramic depends on the aging stability. Okay, if you are using for a longer time the same device, then definitely it is going to show you some lesser characteristics. Then thermal depolarization, if you are providing some very much temperature, like some Curie temperature is there, okay, and beyond that temperature if you are providing, then definitely it is not going to show you that piezoelectric properties. Electric depolarization, mechanical depolarization, these are things. Now I'm coming to one of the application, that is your piezoelectric saw motors. It is in terms of your very micro scale. It is involving a IDT. So it is IDT is nothing but your concept of your structure is there, and it is deposited on the piezoelectric substrate, which is converting the electrical energy into mechanical. So this is, if you will see, the background material is of your piezoelectric. On that thing, this COM type of structure we are making with the help of your aluminum or gold or platinum thing. And when we are providing some voltage to this one, okay, that time it is going to show us this type of deformations. That is nothing but your type of your saw wave or surface acoustic wave it is going to generate. That is not a synchronous way of generation it is making. So if you will see this one, the surface acoustic wave, a small introduction for the saw is there, because we are going to use this saw for development of our actuator thing. So it is nothing but propagates along the surface. If you will check it directly, you can understand with the the middle figure. So once the IDTs are there at that end, and we have given the voltage thing, and it is going to provide the deformation like this one. So it is slowly, it is moving into other end side. So what happens in that case, if you will see the particle motion it is making, how it is making, the lower figure it is showing. So one of the particle, it is nothing but anti-clockwise, it is making motion thing. Okay, so this is the things already covered. This is your piezoelectric material, IDT structure, and this type of wave it is generating. Now there are some basic figures are there, basic construction of your saw devices are there, like resonator, 1-port saw resonator, 2-port saw resonator, then delay lines. So piezoelectric material, I will be mainly dealing with your delay line thing. This is your delay line, means what happens, piezoelectric material we have taken, and on that case the IDs we have fabricated like this way, and here this is your transmitting IDT, another side is your receiving IDT, it is there, and in between we are providing with some gap or a area or a active area where we are going to process our things. Either it can be used for the sensor, either it can be used for the actuation purpose. So for that we need to get some resonating frequency. That means at what frequency we are going to get the highest deformation on the surface of the substrate. So for that we are working on the 1-port saw resonators. In that case it is showing that with aperture. Aperture means in this case already I have shown you. So in this case, what is the aperture? What is the this one? I hope yes, here everything is there. What is the aperture is there? Then saw wavelength is there, electro piece, those things you just check it. So in this case, one small table is there. So what happens in that case, we are getting the resonance of your 8.37 megahertz thing we are getting. So after that we have developed that the delay line thing with the resonator thing. We have developed the resonating frequency, and we have gone for the construction of your delay line thing. And then it is coming to the a surface acoustic motor. What I said in previous slide, that this is the whole delay line it has done. Now one slider or a object, a cubical object we have placed at that, the left side figure, you just check it, the top view it is showing. So what it is saying, I already told that this is the delay line area or the active area is there. In that case we are putting this slider, and when we are providing the voltage to this IDT thing, that time it is generating the displacement on the surface of your substrate. And if you are providing a preload to the slider, that time because of the friction thing, it used to start moving. The slider is going to move this one, and it will be moving in the left side direction. That is, which IDT it is activated, that IDT only, that side only it is going to make the motion thing. If you will see it, the functioning is nothing but these are the motion of the saw is there with that thing. How it is nothing but the upper side there is a arrow. If you will see that elliptical motion thing, top side one arrow is there, it is nothing but it is making the left side motion, and bottom side arrow it is making the right side motion. What happened in the top side arrow, it is having the highest friction and highest velocity, and bottom side is the lowest velocity. So because of the highest velocity thing, it is pulling that slider or that object in the activated IDT side. Okay, so this is nothing but yes, this is nothing but one of the conventional saw is there. So what happens, they have some bulky arrangement it has done, like if you will see, the motor is only up to, if you will check it, that white area is there, no? Okay, in that case only that bottom side is only that saw motor, but to function it, it has taken a huge assembly they have done. Now to reduce that assembly, I started proposing like two ways we will be actuating that thing. So to both side we have used that piezoelectric starter, and in between we have placed that slider thing and started providing the voltage to the IDTs, and it has started working with this thing. And for that thing we have seen, so these are the some of the, this is for validating the results whether it is working or not. So we have started working on a small ball thing we have kept on that wafer thing and how it is moving. Now this is the thing here. If okay, this is moving. No. Okay, fine. So this is the whole structure. It is nothing but a conventional saw motor is there, or saw actuator is there. Do you know what is the structure sizes? This the width of this IDTs, the first left side top picture what I am showing. In that case, the IDT width is around only 75 micrometer. Okay, so that's why you can figure it out how much total device will be. It is in terms of your mm, in terms of millimeter. Whole device will be in terms of your millimeter thing. Now in that case we have got some good results. The displacement of your slider is there, and it is showing something like with the 5 microseconds it is able to move around 290 nanometers. And so dual friction, so that is the dual friction drive we have proposed. In that case what is doing, so both sides you are providing the actuation. One is the starter 1 at the bottom and starter 2 at the top, and in between we are providing the slider thing. So what happens in that case, as you have seen, there was a bulky arrangement was there to make motion in terms of your conventional devices. Now because of this thing, whole arrangement we are able to remove. And if you will see it, okay, so just check it directly. I'm coming to this one. Okay, yes, so this is one of the results I'm showing you. See, this is the conventional one. In conventional one we have kept that slider thing and this piezoelectric thing. Now it is making motion. If you will see, this is also making motion, top one. And this is our proposed one, the dual drive surface sensitive web motor. This one, both side it is able to provide the actuation thing, and it is becoming little quite bit faster, and this way we can able to move that thing. Now, so yes, because this is the only function thing I have shown you, then how you are going to control in which direction your motor, it is the slider, it is going to move it. So that's why there is 4 side we can take it. In that case, if you will say the controlling unit it has given with that thing, switch 1 for what it is working, switch 2 for what it is working. If you will providing the switch 1, then if you will getting this one, then the left side it is going to make motion. Then switch 2, that is the right side. So switch 3, if you will check it, the connections, it is nothing but showing you how it is going to make the 2-axis motion. So that way that was only making the horizontal or linear motion thing. Now suppose we are providing the cylindrical shaft. In that case we can able to make the linear motion as well as rotational motion thing. So with this thing, it is nothing but showing you only the linear motion, that is 80 microsecond. By the end of 80 microsecond, it is of your 90 nanometer displacement it has done. So now it is nothing but this one making the rotational type of motor. These are also the IDT structures, everything it is in terms of a micrometer, and the device it is total of your total millimeters size. This one also it is having some control units. Okay, now it is coming to the how we are going to fabricate. So we have taken the piezoelectric substrate thing, and as when we are taking this piezoelectric substrate from the industry, some from market, there is a chance that it will be having so many dust, so many oily object on placed over that substrate thing. So for that thing we will be cleaning this one in terms of your clean the wet bench process thing. Okay, so after that we are providing the photoresist coating. What it is doing, so with the spin coater we are with either the 2000 rpm or 4000 rpm, a nanometer thickness of your coating we are doing. That is, in our case we have used AZ5214 photoresist we have coated. After that, it is gone for the lithography. Okay, so it is ultraviolet lithography. So that is in that case we are transferring that IDT masking on the surface of your this piezoelectric substrate. Then we have developed, we have deposited the aluminum through the thermal evaporation. In that case, I have used that E-beam evaporation also. Now, see what happened with all the process is over. After that, we are using for the clean wet cleaning. We are using with that thing. All other things it is removed. Only our structure it has came to final deadline. So this one is the practical one. Those things I have virtually I have shown you. This one, the photo of the raw piezoelectric substrate I have taken. There is a cut is there, crystal cut is there, and after that lithography thing, it will be looking like this one. This is taken images. After that deposition of aluminum material, and after Batman's lifter process, it is going to give you the structure of this thing. Okay, so after that the slider, how it will be fabricated. We have taken two silicon substrates, then we have bonded that thing with the bonding process, silicon bonding. Then again the same photoresist coating we have used. Then we have given the structure, the cylindrical projections we have given photolithography way. And after that we have done the dry etching. In dry etching way we are able to get this structure. So this is the thing. If you will see it, fabrication slider thing it is given. So in that case, these are the, if you will check it, there are some dimensions are there in terms of micrometers it is there. This is also some micrometer weight is given. Okay, finally if you will check it, so this one we are doing the dicing thing. Okay, because I have because we are doing the R&D thing, that's why we have taken some of the this delay line I have given quite huge, but it is when we are going for the practical application, it will be you need to minimize this one, this delay line thing. These are the by dicing thing it has done. Finally you will be getting one of the delay lines like this thing, but this structure should be minimized, because whatever the delay line I have given, it can be become half, then only it will be efficient. When we came to know after the realization of your results, because it need to be realized, optimized. Okay, then setup we have done for the testing thing, how it is working. Okay, is it working? Okay, so mainly this videos are working with the liquid thing, how it is working thing. Okay, fine. So if you will check it, this is nothing but the one cylindrical thing is given, and with that thing these are the both side piezoelectric substrate it has given, and it is able to make the motion thing. Okay, it is not moving, but I can show you that the videos. Okay, okay, this thing, this way we have got some two patents thing also out of this thing. Now these are the some more examples. So that is, I have narrowed down that thing to my research work with the introduction to this one, and these are the some more piezoelectric actuators are there, that is ultrasonic motors are there. Then USMs it is used for your camera monitoring thing. Then this is also one of the piezoelectric motors. See, this is your thumb, this is the thumb, this is a fingertip. At the fingertip, how it is looking like, how much size it is. This is the scaling thing, piezoelectric motor, how it is looking like. This is a piezoelectric motor, if you will see it. Okay, so these are the some of the examples it is there. So what are the advantages, disadvantages? Okay, so finally concluding this one with this thing, we can able to gone through what is the structure is there, what are the benefits of them. Okay, so that's all from my side. If you have some question, then you can start asking me. Yes.
Thank you, Dr. Behera, for your nice presentation. May I request the participants, if you have any question, so please ask question to our speaker. Participants.
Hello. In case of
yes, yes, ask, हाँ संग्राम जी बोलिए. Please
in
ask
case
questions.
of
What you have query?
acoustic measurement, acoustic sensing. So in that case, viscous drag should be taken into account.
Yes. Basically, it is not only the viscous drag. Apart from that, there are because when we are moving some object on the piezoelectric substrate, that time it is generating some heat. Okay, and those heat thing also you need to consider, because with that thing also the properties of your piezoelectric substrate, it diminishes or it decreases. So that's why there are not only viscous, because some other things also there. Yes. Any other thing?
In case of piezoelectric
Yes.
material, in
Yes.
piezoelectric crystal,
Yes.
the output is very low in case of a piezo sensor.
Yes. Yes. Yes.
So how the output is it required to amplify it in several stages, or
No, basically in this case, in my case, what we have got is as per the results, because what are the simulation things you are doing, from my experience, I can say that it is not 100% it is going to match it. But we can able to match it up to around 45 to 50% only.
there are two parameters there, voltage sensitivity constant and another is a charge sensitivity. So both of them are manipulated, or
No, actually, what happens in this case, we are giving a burst of signal. It is not a continuous signal thing. Burst signal means it is of 100 volts and with the 10 megahertz of the frequency with a single shot. That means once you are touching, and with that thing, it can able to move up to some thing. With the nano steps or the micro steps, it is going to make motion. Because I have shown you some minimum results. If you will go through some of the papers, one of the my IEEE paper is there, then you will be able to see what are the things are there. Yes.
why silicon is used? Why not other semiconductor?
No, actually what happens, because as per the conventional things, we have taken that the silicon things are there, fine. Because in this case, when we have applied for the rotating thing, that time we have used some fiber thing also. It is not only silicon. Okay, so that's why you can use it. It is not only that silicon why you have used, but why it is there, because we can able to see make the cubical structure easily. Suppose any other things will be we are using, then that may damage our piezoelectric device. That's why we have taken that thing in consideration. Okay. Okay, any other?
Sir, my question is little bit different.
Yes, sure.
Hello. Which sensor can be used for detection of adulteration of milk?
Yeah. Okay.
Yeah.
Basically, what happens? Prior to here, I was there in IIIT Dharwad. That time, I got a request from that Milk Foundation, something in Gujarat. Okay. So they were asking me to develop that sensor thing. It is now that person who has asked me, that person is working there in Guwahati. Okay, the same thing, it is using something piezoelectric, and with that thing, some I think like the antigen antibody, that is the bio thing, it is coming into picture. The biotech thing, it is coming to picture when we are looking to adulteration thing. So now he is working on that thing, and in our see, there are some sensors are available. But what happens in that case, maybe some problems they are getting. That's why they are going for some more optimized device for that thing. Okay.
Sir, can I ask one question?
Sure, please.
Sir,
Very float.
Sir, actually, you talked about Liga process.
Yes.
So, what is the minimum dimension that can be achieved using
feedback
Liga?
for will float.
Actually, it is in terms of your Liga thing, it is some micrometers it is coming. Because what happens when I was there in IISc Bangalore for development of my device, that time also they are optimizing, because see, it is in that, in this MEMS thing, till now there is nothing is standardized thing. I can say only up to the micrometer thing, the Liga thing. No, in that Liga process, it is up to the micro thing. They have not gone to up to nano thing, because when it is going to nano thing, because whatever the things it is there, directly we are not doing any not etching that thing through the some machines. Rather, we are using the chemical compositions. So when we are going for the chemical composition, suppose you are putting a straight line, but you are not going to get that straight line. Instead of that thing, you will be get some rough surfaces of that thing. That's why till now it is in terms of some micrometer it is there.
Sir, what kind of device we can realize, means what kind of device we can think when we go for Liga process? Because Liga process, I think it is used for making small gears.
Yes, small gears, and your valves also there. Some for the valve thing, like some blood pressure, something it is there for, you know, some pumping that blood to heart thing. For that thing also they are using that that actuator thing. So those developing those actuators also, that pump thing, they are using this Liga process. There are two ways that I already told you, that the fabrication of your top to bottom and bottom to top approach. But second is your this one Liga thing. So what happens in that case, the top to bottom, there is a chance of breakage. That's why they're directly taking this one and going for this Liga process thing.
Okay, sir. Thank you, sir. Thank you, sir,
Okay.
for answering.
Any more question from any of you? I think everyone.
Hello.
Yes, anyone?
Yes, sir. I have questions related to measurement. So, whatever the small device when I am preparing, how will do when measuring all that? How will measuring all the parameters?
Oh, there are some high-end equipments are there. High-end equipments are there. With that, we can able to measure it. Okay, because that is nothing but a characterization part. So in characterization part, even you know, you will start characterizing with the surface profile. Suppose if you are developing some sensor thing, what is the surface profile? Whether it is some rough surface is becoming, because it is going through so many chemical etching process, chemical deposition process. Once it is coming to final stage, it is giving you some different results. If the piezoelectric substrate is not smooth one, then definitely you are not going to get the exact results. That's why they started with the surface profile thing. After that, they are realizing the electrical characterization thing, mechanical characterization thing, those things they are making. Okay, so high-end equipments are there for the measurement of this thing. Yes.
Thank you.
Okay.
Okay, thank you, Dr. Behera.
Thank you, sir.
Thank you for your nice presentation.
Okay,
and
sir.
share time with us. There are faculty from all over the India, so if in future they want to contact you, then if you want to share your email ID or something, then you can do it, so that in any confusion, any problem, they can share their problem with you. So can you write your email ID to your in the chat box?
Yes, someone is.
Chavilal Singh.
Yes, sir. Sir, any special type of software for simulation purpose of sensor?
Yes, console multiphysics is a very handy one. Though I'm not doing the advertisement of that software, but I'm using. I have already used for my PhD, and till now my research students, they are using that thing, and I'm quite satisfied and convinced with the results of the console thing. And second one is the ANSYS is there, but you need to know some programming with that thing.
Okay, sir. Thank you, sir.
In previous session, ma'am also tell about the ANSYS and multiphysics. So thank you all, sir. Chandan?
Yes, sir.
One photo plays, everyone plays on your camera for a minute so that we can take a snap. We can include a snap with you so that we can synchronize you in future. Okay? So, present participants, please turn on their camera for a minute only.
So please unmute your camera so that I can take picture of all the participants. Yes, sir. I've taken it, sir.
Okay.
Thank you, sir, for this presentation. The presentation was very informative. Even I have done your classes also. So this subject was really very close to my research work also, and also to my interest also. So it was very informative, and I hope everyone has enjoyed this session. Thank you, sir.
So tomorrow session will start at 10 a.m. sharp. And for any information, a link, etc., all of you can visit our website. We can update everything in website. Okay? Thank you.
Okay, sir. Thank you.
Tomorrow onwards we'll get the yesterday.
Thank you, sir.
Naharka Sethi, you want to say something?
Yes, sir.
Say.
Sir, so tomorrow onwards we will have the link from website itself, or we will get that in our mail.
What link? Your voice is not clear.
This FDP link will be sent in our mail like for today, or we will get
Okay. I send on the mail, but some complaints I will receive, sir, that is not received in my mail. I already sent to your mail, okay, in night hour, and also updated in the website. Okay.
Yes, sir. Yes, sir. Okay, sir. Tomorrow we'll also get that mail.
10 to 11:30, and then second session 12 to 1:30, and third 3 to 4:30. And on Sunday, I want to I received several requests for Professor Guy Dhane sir today morning session, and I talked to him. They take a half-hour session on Sunday morning. Sunday morning, they take a half-hour physical session, some exercise or some breathing exercise like that. Okay? So Sunday morning, we will join at 9:15 to 10 one special session, and then there are 3 regular session also. Okay?
Okay.
Okay. That is 9:15 to 10 session.